Now let's look at a few questions on elasticity. Just a few simple problems. The first question here says a force of 1.8 newtons. The first question says a force of 1.8 newtons extends a wire by 0.4 centimeters. So what that means is simple. Our F1 is 1.8 newtons and our first extension produced by that first force is 0.4 centimeters. The questioner says, what force will produce an extension of 1.25 centimeters in the stem elastic material? Now, from Hooke's law states that provided the elastic limit is not exceeded, the force applied to an elastic rubber is directly proportional to the extension produced. So provided the elastic limit is not exceeded, F is directly proportional to E. That makes it very simple for us to find a relationship between F and E. Change this from variation, change it to an equation by introducing your K. F will be equal to KE. Can you see that, senior? F will be equal to KE. So that means KE is equal to F. And if KE is equal to F, it means what? K is equal to F over E. It means K is equal to F over E. Meaning that the ratio force applied over extension produced, meaning that the ratio of force to extension produced, let me say it this way, meaning that the ratio of force applied to the extension produced in any elastic material is always constant as long as the elastic limit is not exceeded. What this means is that F1 over the extension produced by F1 will be equal to the same thing as F2 divided by the extension produced by F2, which is E2. That will also be the same as F3, another force, divided by the extension produced by that force, on and on like that. That's what the Hooke's law means. So let's now go ahead and use this to answer this question. So it means F1 over E1 is equal to F2 over E2. We know F1 1.8 newtons. We know the extension is produced is 0.4 centimeters. We now need F2, a second force, which will produce an extension of 1.25 centimeters. So what you do here is just simply cross multiply, make F2 subject to the formula. You will get 0.4 F2 is 1.8 times 1.25, and F2 will be 1.8 times 1.25 divided by 0.4. So that solves question 1. Now question 2 says a force of 50 Newton increases the length of an elastic material from 20 meters to 20.01 meters. Now calculate the force which will increase its length from 20 meters to what? From 20 meters to 20.05 meters. Now this is very simple. What is the extension in this case? We know the force, F1, 50 newtons. But what is the extension in this case? That will be our E1. The extension in this case is 20.01 minus 20. That gives you what? 0.01 meters. So my first extension, E1, is 0.01 meters. Can I write that? We're going to be consistent. Okay. My first extension here is 0.01 meters. Also, the question says another force, F2, increases the length of the elastic wire from 20 meters to 20.05 meters. So in this case, the second extension will be 20.05 meters minus 20 meters. That gives us what? L3. Let's call this L3. L3 minus L1, which is the original. L1 is the original length of the elastic wire. And that gives what? 0.05 meters. So we know our E2, we don't know our F2, but we know F1 and E1. So using Hooke's law, the ratio F1 over E1 will be equal to F2 over E2. That gives you what? 50 over 0.01 is equal to F2 over 0.05. And that will be equal to what? When you cross multiply, what do you get? You will get 0.01 F2 is equal to 50 times 0.05. Senior, are you getting this, please? So that gives you what? 50 times 0.05 over 0.01. So our F2 will be equal to, you get that yourself and put nothings in front of it. That ends question 2. Let's go to question 3. Question 3 says, the extension in a spring when 5 gram weight was hung from it is 0.56 centimeters. So sometimes our force can be written in grams. 5 gram weight. All of this symbol is not your business, but let's just put it. So the extension produced by this weight is 0.56 centimeters. So we know our F1 and we also know our E1, which is the extension that F1 produces. Can you see that now? The question says, if Hooke's law is obeyed, what is the extension caused by a load of 20 gram weight? So that means we have F2. We have F2, which is a load of 20 gram weight. We need the extension that it produces on the elastic wire or on the spring. That's very simple. Using Hooke's law, F1 over E1 is equal to F2 over E2. Using Hooke's law, F1 over E1 is equal to what? F2 over E2. Let's substitute now. I want to keep the page open so you can see as I pick. F1 is 5 gram weight, but throw away this so that it will not confuse us. Since it's the same for both masses, we have no problem with writing just the constant. So F1 5, okay, or let me keep it on the left. F1 is what? 5. E1 is 0.56. F2 is what? 20 gram weight. F1 is 5 gram weight, F2 is 20 gram weight. 5 gram weight, 20 gram weight. This will cross out, so we don't need all that anymore. So it says F2 is 20 gram weight. We need the extension it produces, so you just cross multiply. When you cross multiply here, what do you get? 5 times E2 is 20 times 0.56. Let me try and be economical here because subsidy has been removed, so we should just try and manage in everything we do. 20 times 0.56 over what? 5. So that will give you the extension produced when the 20 gram weight is hung on the spring. Okay, that ends question 3. Question 4 now says a 10 gram mass placed on the pan of a spring. A 10 gram mass placed on the pan of a spring balance causes an extension of 5 centimeters. So let's go straight and fill that in. A 10 gram mass, number 4, a 10 gram mass, so F1, 10 gram. Never mind that it's not in Newton, you understand? Just leave it like that. Causes an extension of 5 centimeters. So we know F1, we know E1. The second part of the question says, if a, can you see this? If a 15 gram mass is placed on the pan of the same spring balance, the extension is, so it's the same thing. It's the same thing as the previous question. So if you now change the force to a 15 gram mass, what is the extension produced? That's what we are being asked. So let's go straight. From Hooke's law, the ratio F1 over E1 is equal to the ratio F2 over E2, because the ratio of force to extension is always constant. That means 10 over 5 should give us the same thing as 15 over E2. So let's cross multiply. What do we get when we cross multiply? I'm going to manage that space. So 10 times E2. 10 times E2 gives us what? 10 E2 is equal to what? 5 times 15. So, senior, are you getting this? Extension, force, and co, they are not things that anybody ever gets wrong. Just look at it very well. So 5 times 15 over 10 will give you the extension produced when the mass is changed to 15 grams. You get your answer in centimeters. You press your calculator for that. Let's go to question 5. Question 5 says, a spiral spring extends from a length of 10 centimeters to 10.01 centimeters. A spiral spring, when a force of 20 Newton is the force, a spiral spring goes from its original length, 10.00 centimeters, to another length, 10.01 centimeters. So here, the extension produced here will be called E1, extension produced by this force, 20 newtons. So E1 is L2 final length minus original length, which is 10.01 centimeters minus 10.00 centimeters. Can you see that, Sina? 10.01 centimeters minus 10.01 centimeters minus 10.00 centimeters. So our first extension is 0.01 centimeters. So keep that in mind. You have F1 now and you have E1. So this is my E1. Let me try and write this here again. So let's go to the second part of the question. It says, okay, the length increases from 10.00 to 10.01 when a force of 20 Newton is applied on it. Okay, it now says calculate the force constant of the spring. That brings us to another part of elasticity. Force constant, let me define that for you. Force constant of a spring. Force constant of a spring is called K. Force constant of a spring is called what? K. And it is equal to, it is defined as the load. This is the load or force. The force constant of a spring is the load or force. We can call it load, we can call it force. It is the load or force which produces an extension of 1 meter in the material. The force constant of a material is the load of force which produces an extension of 1 unit length. Sometimes we say this as 1 unit length. You understand? Instead of saying force constant is the load, the force constant of a material is the load of force which produces an extension of 1 meter in the material. I can say the load, force constant is the load or force which produces an extension of 1 unit length in the material. You understand? 1 meter is the same thing as 1 unit length. So say it how you like. The English is not a problem. Just get the concept right. So here now we using F is equal to KE. Every force and the extension produced, every force and the extension it produces are related. In any elastic material, every force and the extension produced by that force are related by the equation F is equal to KE. So in this question now, 20 newtons produces an extension of what? 0.01 meter. Am I right? Is it meter? Okay, centimeters. I have to change that because we cannot use centimeter. This will be a red flag in my mind that, I cannot use centimeter, which is not in SI unit, with newtons, which is in SI unit. So I have to go change this centimeter to meter. Let's do that here. We can do that here. So 20 newton is equal to K times 0.01. Centimeter to meter, you divide by 100 and that changes it to meter. So K times 0.0001 meter is equal to 20 Newton. So going forward, 20 newtons is 0.0001 meter times K. Let's put that on the left. 0.0001 meter times K is equal to 20 newtons. I just rearranged. So my K now will be 20 newtons divided by 0.0001 meter. I'm trying to keep the units so you can see how we get the unit for force constant of an elastic material. So that gives you what? You write your answer and you put the value or the SI unit, Newton per meter. You can use Newton per meter like that, or you can use it like this. Anyone that you please is okay. So that answers question 5. Let's go to question 6. Question 6 says the total length of a spring when a mass of 20 grams is hung from its end is 14 centimeters. So you have to be careful here. Let's say this is the spring. Now, when a mass of, let's say this is the spring. When a mass of 20 grams is hung from it, it will expand, it will expand. Are you getting what I'm drawing? It will increase in length. So let's say this is its original length. This one will be its original length. Let's say this is its original length, L1. But when the mass of 20 grams is hung from it, that original length will increase from L1 because there will be some expansion. There will be E1, which is the first expansion produced by the what? By the 20 grams. So when the 20 gram mass is hung, the length of the spring will increase because the 20 gram mass will cause an extension to be produced and its length will increase. They now said the total length produced, the total length of that spring, when you add the extension produced, is what? L2, which is 14 centimeters. So that means to get E1, that means in this question now, we know F1, 20 grams. But to get our E1, we have to use 14 minus L1. Are you getting what I'm saying? Because 14 is the final length and L1, we don't know it. We don't know the original length. Let's just leave it like that. That the first extension E1 produced is going to be this total length minus the original length of the rubber. Because we only know that the total length produced or the total length reached after hanging 20 gram mass is 14. We don't know the initial length, which is the original length that the rubber had before we placed this mass. So we leave this expression as the value of our what? Of our first extension. So I know F1 now and I know E1. Take note of this question, very important. Now the next part says, while its total length is 16 centimeters, when a mass of 30 grams is hung from the same end, calculate the unstretched length of the spring, assuming Hooke's law is obeyed. So we are going to draw another diagram. Let me draw another diagram. The same spring, the diagram will now tell us, the second diagram will mean that in the same spring, when you hang a mass of what? A mass of 30 grams. In the same spring, when we hung a mass of 30 grams, the total length produced was 16 centimeters. So this is the original length of the spring, L1. But another extension will be produced. Another extension will be produced when we hang a mass of what? When we hang a mass of 30 grams. So look here now. Let's say this is my hook and my 30-gram mass is hung here. So when my 30-gram mass is hung here, the question says it produces an extension E2. It will produce another extension E2. But I don't know E2, just like I don't know E1. I just know that the final length produced, the final length that I get, the final length of the string, I just know that the final length of the string, L3, is what? 16. So in this case too, I will say the force applied. In this case too, what I will say is simple. I will say the force has now changed from 20 to what? 30. So the second force applied, which is the mass, is 30 grams. But my second extension, E2 produced, must now be 16 minus the original length of the string. Are you getting the logic, senior? Because my second extension produced must be L3 minus L1. L3 meaning final length produced by 30-gram extension or by the 30-gram weight. L1 meaning the original length of the string. So that gives me my E2 as what? 16 minus L1. In this question, we have to find L1, which is very easy to do. We do the same thing. We have to find L1. Let's go ahead and find L1. So using F1 over E1 is equal to F2 over E2, provided the elastic limit is not exceeded. According to Hooke's law, this ratio will always be a constant, even if you go on and on. Is that clear, senior? So that means I'm going to write 20 over E1, which is 14 minus original length, is equal to 30 grams, 30 over E2, which is 16 minus original length. Don't forget, the weight is mass times acceleration due to gravity, but G can cancel G. So we can just leave 20 and 30. Can we go ahead now and get our original length of the spring? The original length of the spring, we do 30 times 14 minus L1 is 20 times 16 minus L1. Can you see that? So this gives me 420 minus what? Minus 30 L1 is equal to 320 minus 20 L1. So what will I get for this? I will get 420 minus 320. I'm collecting like terms, is equal to minus 20 L1 plus 30 L1. Can you see that? So 100 is equal to what? 10 L1. Minus 30 minus 20 plus 30 is 10. So take note of that. I can rearrange. 10 L1 is 100. L1, which is the original length of the spring, is 100 divided by 10. So L1 is 10 centimeters. So the original length of the spring, which is also called the unstretched length, the original length or unstretched length. Don't let the grammar distract you. They are all simple stuff. Or the unstretched length of the string. The unstretched length of the spring is equal to 10 centimeters. So take note of that question. Very, very important. Let's go to question 7 now. In question 7, it says, a force of 100 newtons stretches an elastic string to a total length of 20. I think question 7 will be the same as question 6. So F1, 100 newton, stretches an elastic string. Let's say the original length of the string, we don't know it, but it stretches it to a final length of what? It stretches it to a final length of 20 centimeters. So L2, 20 centimeters. Now let's go ahead. The question says, if an additional force of 100 newton, additional force of 100 newton means that our F2 will be F1 plus another 100 Newton. That's what 100 Newton plus 100 Newton. That's what additional means. That means we are not removing the first weight. We just added another 100 to it. So our F2 is now 200 Newtons altogether. That's the meaning of an additional length of 100 Newtons. So you are not taking this one away. It's like putting 10 gram mass up and adding another 10 gram mass. So you are not taking away the first mass. You just added another one to the pan of this spring. So our F2 is 200 Newtons. It says if an additional force, it's here, if an additional force of 100 Newtons stretches the string 5 centimeters further, okay, that's another English we have to be very careful with. 5 centimeters further means our second final length, when the weight change to 200 Newton, is just 5 centimeters longer than this one. 5 centimeters further will mean L2, the final length we got here, plus 5 centimeters. So that's L2 plus 5 centimeters, which is what? 20 centimeters plus 5 centimeters. So our L3 will be equal to 25 centimeters. This is very, very important. Please. The question says, find the natural length of the spring. Natural length means the same thing as original length or stretched length. What we need to do is simple. Let's get the extension here. The first extension here is L2 minus L1, like we did in number 6, which is 20 minus L1, because I don't know L1. So I just keep it there, blank. Then the second extension produced here, after reaching a final length of 25 centimeters, the extension produced will be L3 minus L1. L3 being the final length produced by the 200 Newton force, and L1 being the original length of the spring. So this will give us 25 minus L1. So going to our Hooke's law, we say from Hooke's law, the ratio of force to extension is always a constant. So F1 over E1 is F2 over E2. That gives you what? That gives you 100 Newton over what? 20 minus L1 is equal to 200 Newtons over 25 minus L1. So we now cross multiply to get our answer. Let me take this Newton out. We don't need it because I didn't write this. I didn't write the one here, I didn't write the one here. So now this will give us what? 100 times 25 minus L1 is equal to 200 times 20 minus L1. This will give 2,500 minus 100 L1. 2,500 minus 100 L1 is 4,000 minus 200 L1. So let's simplify now. What will this give you? Minus 100 L1 plus 200 L1. I hope you understand that when I bring minus 200 L1 from the left across the equality sign, from the right across the equality sign to the left, it should give me what? Plus 200 L1. So that's, elementary math, senior. I'm sure you don't have a problem with that. So it's equal to 4,000 minus 2,500. This gives me what? 100 L1 is 1,500. 45 minus 25 is 1,500. So L1 is 1,500 divided by 100. The original length or natural length or unstretched length of the spring will be 15 centimeters. Never mind the English. Unstretched length is the same thing as natural length. You understand? English is not always a problem here. Just know they're just changing words. So unstretched length is the same thing as natural length. Natural length is the same thing as original length. They all mean the same thing. So don't let that confuse you, Sina. Let's go to question 8 now. Question 8, we'll take it one after the other. It's an interesting exercise. The next question says, the spiral spring of a spring balance is 25 centimeters long. So in this case, I know the original length of my spring balance. Okay, 25 centimeters long. No, that's not the original length. It is 25 centimeters long when 5 newtons hangs on it. So that's a stretched length. Can you see now? That's not the original length. So I know F1, 5 newton, and I know final length, 25 centimeters long. When 5 newton hangs on it, its length becomes 25 centimeters long. So I don't know what the original length is. I don't have this. Let's go back. Okay, 25 centimeters long when 5 newton hangs on it, and 30 centimeters long when the weight is 10 newton. Okay, good. That's interesting. When we change the weight hanging on it to 10 newtons, the final length becomes 30 centimeters long. So here too, I don't know the original length. I don't know the original length in each case. The original length from which the wire was extended. The question says, what is the length of the spring if the weight is 3 newtons? What is the length of the spring if the weight hanging on it is 3 newtons? Assuming Hooke's law is obeyed. So we need the original length before we can find the extension produced by 3 newtons. Exactly. Okay, I think that's what we're going to do. So here, the extension produced here would have been L2 minus L1. You know, the final length, 25 centimeter produced, minus the original length of the spring before 5 newton was hung on it. So E1 is 25 minus what? L1. E1 is 25 minus L1. In the same way, E2 here also is 30 minus L1. The final length produced when 10 newtons force was hung on it is 30 centimeters. So that means the extension will be 30 centimeters minus the original length L1. We don't know this, so we just leave it there as a letter. So this gives us what? F1 from Hooke's law, F1 over E1 is F2 over E2. So let's go do 5 over 25 minus L1 is what? Is 10 over 30 minus L1 and cross multiply. I hope I substituted that correctly. Good. Everything is okay. So let's cross multiply. What do we get here? You can do any side first. 5 times 30 minus L1 should give you 10 times 25 minus L1. Can you see that? So what do we get here? We get 150 minus L1 is equal to 250 minus 10. 150 minus 5L1. Sorry. 150 minus 5L1 is 250 minus 10L1. So simplifying, what do we get? 150 minus what? Or let's put our letters on the left. Minus 5L1 plus 10L1 is what? 250 minus 150. That gives you 5L1. 250 minus 150 is 100. So L1 is 100 divided by 5. L1 is 100 divided by 5 means L1 is 20 centimeters. The original length of the spring is 20 centimeters. So, okay, we now need the extension produced. We need the extension produced when a force of 3 newtons is hanging on the spring. So that means we want to find the extension when we want to find the extension E3 when the force is 3 newtons. I don't think that should be difficult for us. I don't think that should be difficult for us. Let's use our Hooke's law. We still use our Hooke's law. How do we use our Hooke's law here? We will say F1 over E1 should give us F3 over E3. I can use any one. I can also use F2 over E2 is F3 over E3. I can use any set I like. But let me use F1 over E1 is F3 over E3. What's our F1? Our first force was 5 newtons. And the extension produced will be what? 25. Now that we know L1. Now that we know L1 as what? We now know L1 as 20. So that means the extension produced by the 5 Newton force will be 25 minus 20. So instead of writing L1 now, I can put the value of L1 that I have gotten. So this gives me 5 over 25 minus 20 will be equal to, according to Hooke's law, the ratio 5 over 25 minus 20 will be equal to the same as 3 newtons over 20. 3 newtons over what? 3 newtons over E3. Let me just put it that way. So the extension produced by 5 newton is now 5. 25 minus 25. I now need the extension that 3 newtons force will produce. If 5 newton force produces an extension of 25 minus 20, which is 5 centimeters, I am now looking for what extension will be produced by 3 newton force. So I just put E3. I don't need L3, L1, blah, blah, blah. I just put E3. So let's cross multiply. What does that give us? You know, this is the same thing as, okay, before we cross multiply, let's make it look simpler. 5 over 5 is 3 over E3. So cross multiplying, 5 over 5 is 1 over 1. 1 over 1 is what? 3 over E3. So if you cross multiply here, your the extension produced by the 3 Newton force will be 3 centimeters. 3 centimeters. Take note of that. Okay. What number was that? It says, what is the length of the spring if the weight is 3 newtons? Okay, we are not looking for extension. We are actually looking for the final length when a 3 newtons force is hung on the spring. It says, what is the length of the spring if the weight is 3 newtons? Assuming Hooke's law is obeyed. I'm still on number 8. So let's make corrections there. We got the extension. So we are actually supposed to find the length. So the final length, when the extension is 3 centimeters, the final length will be original length plus extension. That's what? 20 centimeters plus 3 centimeters. So the final length will be what? 23 centimeters. That's the answer required. When a weight of 3 newtons is hung, the final length of the spring will be equal to 23 centimeters. Please watch that carefully. Make sure you understand it perfectly. Number 9 says, a force of 15 newtons stretches a spring to a length of 30 centimeters. A total length of 30 centimeters. Same way, force of what? 15 newtons stretches a spring to a final length of 30 centimeters. So that means it must be coming from some original length that we don't know, but we just know the final length produced. Okay. An additional force of 10 newtons. So additional force means our F2 is just F1 plus 10 newtons, which is what? 15 newtons plus 10 newtons. You are not removing the 15 newtons. You are just adding 10 newtons more. An additional force of 10 newtons stretches the spring 5 centimeters further. In this case too, 5 centimeters further means our last length here, our final length here in this case is just L2 plus 5 centimeters. Just the previous final length plus another 5 centimeters. Are you getting what I'm saying? So that gives us what? That gives us 30 centimeters plus 5 centimeters. And that's what? 35 centimeters. So our L3 is 35 centimeters. The question now says, find the natural length of the spring. Okay, that's simple. We did that in previous cases. The extension produced in this case is going to be final length minus original length. That's 30 minus L1, which I don't know. In this case, the second extension produced will be final length minus original length. So that's L3 minus L1, which is 35 minus L1. So according to Hooke's law, we say from Hooke's law, the ratio of force to extension is always the same. It's always constant. So that means first force over first extension will be equal to second force over second extension. Are you getting what I'm saying? See now, take this very seriously. You know, you have this in objectives and essays so many times in the exam and it looks somehow, but once you know the basics, it will just be ABC to you. So our first force is what? 15 newtons. Our first force is 15 newtons. So 15 newtons force produces an extension of 30 minus L1. 15 newtons force produced this extension. Okay? Now, another force, 25 newtons, produced the extension 35 minus L1. We got that here. 25 newtons, 15 plus 10, produced the extension 35, 30 plus 5, which is what? 35 minus L1. Produced the extension 35 minus L1. Final length here minus the original length of the rubber. So we can remove our n. We don't need it in both cases and cross multiply. When we cross multiply, what do we get? 15 times 35 minus L1. Number 9 is just exactly like numbers 6, 7, and 8. 15 times 35 minus L1 is 25 times 30. Is what? 25 times 30 minus L1. So let me use my calculator here. What does that give us? We'll get 15 times 35, 525. So 525 minus 15 L1 is equal to 750. 25 times 30 is 750 minus 25 L1. 525 minus 15 L1 is 750 minus 25 L1. So put this together. Minus 15 L1 plus 25 L1 minus 15 L1 plus 25 L1 is 750 minus 525. So that's 10 L1 is what? 750. That's 50 minus 25, that's 25. 7 minus 5, that's 2. So L1 is 225 over 10. What does that give you? What does that give you, Sina? That gives you L1 is 22.5 centimeters. So the original length of the spring is 22.5 centimeters. Question 10 says, a piece of rubber 10 centimeters long stretches 6 millimeters when a load of 100 newtons is hung from it. What is the strain? That brings us to another part of elasticity. Number 10. Strain. Let me define it first. The strain on an elastic material is the extension per unit length. Is the extension produced per unit length. Or let's just simply say extension per unit length of the material. Strain is the extension per unit length of a material. So we always write strain. Sometimes we simply write strain. Sometimes you can see it called tensile strain. Tensile strain is extension over original length. So if something is 50 centimeters and it extends by 2 centimeters, the strain will be 2 centimeters over 50 centimeters. So you can see this is 1 over 25. Strain has no unit because it's a ratio of 2 lengths. So here, the original length, in this question, the original length of our material is 10 centimeters. The extension produced when it is extended is 6 millimeters. I hope I'm getting that right. 10 centimeters long, stretches 6 millimeter. When a load of 100 Newton is hung from it, okay, the load that causes this, extension is 100 Newtons. Okay, but it's a pity we actually don't have any business with 100 Newtons if we need strain. So I'll just say tensile strain is extension over load. That's what 6 millimeters over 10 centimeters. But do it well. You can't divide millimeters by centimeter, except you either change both to centimeter or change both to millimeters, anyone you choose. But I think I'll find it easier if I change 10 centimeters to millimeters. So this is 6 millimeters. The strain will be 6 millimeters over 10 times 10 millimeters. That's 6 over 100. Millimeter, we divide millimeter. 6 over 100 is equal to 0.06. My strain, the tensile strain on the elastic material, is 0.06. There's no unit, just 0.06. Number 11 says a load of 20 newtons on a wire of cross-sectional area 8 times 10 raised to the power minus 7 meters squared. Force or load 20 newtons. Cross-sectional area of the wire 8.0 times 10 raised to the power minus 7 meters squared. Produces an extension of 10 raised to the power minus 4 meters. The extension produced by the load is 10 raised to the power minus 4 meters. The question says calculate the strain. The question says calculate the Young's modulus for the material if the wire. Calculate the Young's modulus of the material of the wire. Calculate the Young's modulus for the material of the wire if its length is 3 meters. So that's a simple question. The original length of the wire, 3 meters. One thing you need to know here is that Young's modulus, sometimes denoted E. Young's modulus is tensile stress over tensile strain. Tensile stress over what? Tensile strain. Tensile stress is force on an elastic material divided by its cross-sectional area. Tensile strain is extension over length. So that means if I do this, like we do normal division to rearrange, I'll be doing Young's modulus is F over A divided by E over L. That will give me Young's modulus is F over A times L over what? E. So Young's modulus is what? That means Young's modulus is FL over EA or AE, anyone you choose arrangement. So F, what's my F? Let's now find the Young's modulus. What's my F? My F is 20 newtons. My F is 20 newtons. What's my L? 3 meters. What's my A? 8.0 times 10 raised to the power minus 7 meters squared. What's my extension? The extension produced is 10 raised to the power minus 4 meters. So I'll just go ahead and put the value 10 raised to the power minus 4 meters. That's what that gives me. Meter we divide meter. Then when I simplify, I'll get 60 newtons divided by 8 times 10 raised to the power minus 7 plus minus 4. will give me minus 7 minus 4 meters squared. And that's what? 60 Newton over 8 times 10 raised to power. Okay, that will give me 60 newtons. That will give me 60 newtons divided by 8 times 10 raised to power minus 11 meters squared. So you simplify. What is 60 over 8? I think that's the main division there. 60 over 8 is 7.5. So this is 7.5 Newton divided by 10 raised to power minus 11 meters squared. That will give me 7.5 times 10 raised to power minus 11. When you take it up, it becomes plus 11 Newton per meter squared. Your answer for the Young's modulus is 7.5 times 10 raised to power 11 newtons per meter squared. Take note of that question, very important. Number 12 says the tendon in a man's leg. Number 12 says the tendon in a man's leg is 0.01 meter long. You don't have any business with the technical name tendon. Just see it as an elastic spring. You understand? So the length of the elastic spring is 0.01 meters. 0.01 meters. Next part says if a force of 5 newtons stretches the tendon by 2.0 times 10 to the power minus 5 meters. Okay? If a force of 5 newton stretches the tendon, produces an extension of 2.0 times 10 raised to the power minus 5 meters. If a force of 5 newtons stretches the tendon by 2.0 times 10 raised to the power minus 5 meters, calculate the strain on the muscle. Calculate the strain on the muscle. Okay, what we need here now is strain. Strain, like we know, strain is what? Extension over length. So that means the strain on the muscle is 2.0 times 10 raised to the power minus 5 meters over 0.01 meters. Let's do that carefully. We don't need the force. That's 2.0 times 10 raised to the power minus 5 over meter. We already take out meter. So 2.0 times 10 raised to the power minus 5 over 1 times 10 raised to the power minus 2. This will give 2.0 times 10 raised to the power minus 5 times 10 raised to the power 2. 1 minus 2 goes to the top. It becomes plus 2. So 2.0 times 10 raised to the power minus 5. Okay, let me write that neatly. 2.0 times 10 raised to the power minus 5 plus 2. 2.0 times 10 raised to the power minus 5 plus 2. That gives me what? Strain is what? 2.0 times 10 raised to the power minus 3. The strain on the tendon is 2.0 times 10 raised to the power minus 3. 13. If the stress on the wire is 10 raised to the power 7 Newton per meter squared. Let me go ahead and jot that down. It's good practice in physics. Stress is equal to what? 10 raised to the power minus 7 Newton per meter squared. The stress on the wire is 10 raised to the power minus 7 Newton. Okay, 10 raised to the power 7, not minus 7. I'll correct that. The stress on the wire is 10 raised to the power 7 Newton per meter squared. The questions, and the wire is stretched from its original length of 10 centimeters to 10.05 centimeters. Its original length L1 is 10 centimeters. 10.00 centimeters. Its final length L2 after being stretched, its final length is 10.05 centimeters. So we can get the extension produced here. The extension produced is L2 minus L1. Okay, the extension produced is L2 minus L1. So that's 10.05 minus 10.00. 10.05 minus 10.00 gives us an extension of 0. Gives us an extension of what? 0.05 centimeters. Okay, let's keep that. The Young's modulus of the wire is Young's modulus of the wire. Okay, Young's modulus of the wire. Young's modulus, like we did before, Young's modulus is tensile stress, tensile what? Stress divided by tensile strain. Young's modulus is tensile stress divided by tensile strain. So Young's modulus of the wire will be force over area. We don't need this formula because we've been given the stress already. 10 raised to power 7 Newton per meter squared divided by extension over length. This one is the only one we need to work. So let's go ahead and do that. Okay. That's 10 raised to power 7 Newton per meter squared divided by extension is what? 0.05 centimeters. The extension is, or let's go and work out the strain and just bring the answer here. I think that will be neater. Or let's do it together. Any one of the two is okay. So 10 raised to power 7 Newton per meter squared divided by 0.05 centimeters over 10 centimeters. So as you can see here, centimeter will cut centimeter, they will not be there again. So you know how we do division of fractions. 10 raised to power 7 Newton per meter squared. 10 raised to power 7 Newton per meter squared. This 10 will go up. This 10 will go up here. So times 10 over 0.05. Centimeter has cancelled centimeter. They are not there anymore. So we are just evaluating the denominator side, starting from the units. Then 10 will go up. So that gives you what? What does that give you? That gives you Young's modulus is 10 raised to power 8. 10 raised to power 7 times 10 raised to power 1. Just add 7 to 1. Bases are the same. Add powers. 10 raised to power 7 times 10 raised to power 1 is the same thing as what? 10 raised to power 7 plus 1. I'm skipping some of the maths so we can finish quickly. Is that clear, senior? So that gives us 10 raised to power 8 divided by 0.05 Newton per meter squared. So you will get your answer. 10 raised to power 8 is just 10 raised to power 8 is just 1 and 8 zeros. You understand? But if you use indices, you will get 10 raised to power 8 over 0.05 is 5 times 10 raised to power minus 2 Newton per meter squared. I think that is more ideal. So this gives us what? This gives us 10 raised to power 8 times. This gives us, you can slot 1 behind 10 and get 1 times 10 raised to power 8. So you now change it to 1 over 5 times 10 raised to power 8 divided by 10 raised to power minus 2 Newton per meter squared. That will give you 0.2 times 10 raised to power 8 minus 2. Are you getting it? That's 8 plus 2. Know how to evaluate these powers. They are very, very important. So that's 0.2 times 10 raised to power 10. Your answer is 0.2 times 10 raised to power 10 Newton per meter squared. 0.2 is 2.0 times 10 raised to power minus 1 times 10 raised to power 10 Newton per meter squared. Can you see that? So that gives us what? That gives us 2.0 times 10 raised to power minus 1 plus 10. 2.0 times 10 raised to power minus 1 plus 10 Newton per meter squared. And that's 2.0. The Young's modulus is 2.0 times 10 raised to power 9 Newton per meter squared. So sometimes you know the formula, but if you are not very careful with the indices, you might make a mistake. Okay, let's continue. Question 14. Question 14 says, a spiral spring of natural length 30 centimeters. Spiral spring, natural length. Let's write that down. I'm just going to write L1. A spiral spring of natural length 30 centimeters. And force constant 20 Newton per meter. Okay, force constant, that's K, 20 newtons per meter. 20 newtons per meter force constant. A spiral spring of natural length 30 centimeters and force constant 20 newtons per meter is compressed to 20.0 centimeters. Do they mean 20.0 or 20.01? Because 20, okay. It's compressed to 20.0 centimeters. Okay, that's correct. It's compressed means that its length is reduced to a final length of 20.0 centimeters. The original length is 30 centimeters, which is the same thing as 30.0 centimeters. The question says, calculate the energy stored in the spring. All right, now let me introduce one concept to you here. We call it energy stored in an extended string. Okay, good. Now let's look at this. Look at this spring. Let's say I put a nail into the wall here and I tie a string to it. The string has this original length. Can you see that? Let's say this is the original length of the string, L1. Is that clear? Now, after I extend, if I apply some force to this end and I use it to pull the string in this direction, if I apply some force at this end, and I use that force to pull the string to the right hand side from the wall, what will happen? The length of the spring will increase like this. Take note of this very well, senior. Very important. Let's say the length of the spring now increases to this point. You know that I have gotten some extension. You understand? The force has produced some extension. Now, when I do that, what I have done is that I have used some force to do work on the spring. And work done is force times distance. In this case, our distance is the extension. Are you getting what I'm saying? Let me remove these ones because we are not comparing lengths. So, the work that my force has done on the elastic material will be equal to what? Force times distance traveled by the force in the direction of the force, which is the same thing as force times extension in this case. The distance moved by my force is the extension produced in the spring. So, that work done is usually stored. That work done in physics, we say that work done is usually stored in that spring as elastic potential energy. The work done is usually stored in the spring or in that elastic material as what? Elastic potential energy. So that when you release the spring, let's say a stone is tied to the end of the spring here. When you release the spring, all that potential energy will be given to the stone as kinetic energy. That's what normally happens in springs when work is done on them and the work done is converted to elastic potential energy, which is converted to kinetic energy of a stone and released. That's what happens in your catapult when you try to kill a bird with a stone tied to one end of a rubber on a catapult. So in this question now, they are telling us that the same thing happens when this string was if the spring was compressed by some extension and some applied force. That's the same thing that will happen. Work done is also F times the compression. So what they are now asking us in this question is that we should calculate the energy stored in the spring. So very simple. Energy stored in the spring is Fe. Energy stored in the spring is what? Fe. Energy stored in the spring is Fe. Fe. And we know before that what? We know that Kf is equal to Ke. But we always know that F is equal to what? Ke. So we can say energy stored in this spring is equal to Ke times E. Are you getting what I'm saying? That gives us energy stored in the spring as Ke squared. But in physics, we always consider that more accurately, the force is not maximum at the beginning of the extension. The force is not maximum at the beginning of the extension. The force starts from 0, increases gradually until it gets to a maximum when the string is fully extended. So we kind of use some average. Introduce some average to say that the work done is average force applied to the spring times the extension. So this will give us half Ke times E, which will give us what? Half Ke squared. So in this question now, the energy stored in the spring will be half Ke squared. That's half times 20. Half times what? 20 Newton per meter. That's half times 20 Newton per meter times extension. Extension will be, let's get our extension from here. What will our extension be? We know our values. So our extension will be what? L2 minus L1. We didn't find the extension before, so let's get it. That will give you what? L2 minus L1 will be 30 centimeters minus 20 centimeters. So your extension is 10 centimeters. Take note, centimeter is not the SI unit of length. So you divide it by 100 to change it to 0.1 meters. So our extension is 0.1 meters. Let's slot that in here. 0.1 meters times 0.1 meters, because we have E squared. Is that clear? So meter will cross meter. Meter will cross meter. You have just Newton and meter left in your SI unit. So that gives us what? That gives us 10 Newton times, I'm doing 2 here 1, 2 here 10. That gives us 10 Newton times 0.1 times 0.1 meters. So that gives us 10 times 0.01 meters. And that's what? 0.1 Newton meter. Which gives you what? Energy stored in the spring as elastic potential energy. Energy stored in the spring as elastic potential energy will be 0.1 joules. So energy is measured in joules. Please take note of this question. Notice how the half comes in, and keep that in mind. Energy stored in an elastic spring. So take note. Let me jot that in a circle for you. Energy stored in an elastic spring as elastic potential energy is half Ke squared, or half Ke squared, or half Fe, if you have the force and the extension produced. So take note of this scenario. Very important. Let's go to question 15. We are moving forward. Let's go to question 15. Question 15 says, an elastic string of force constant 200 newtons per meter. Okay, I think that's going to almost be the same like the previous, or similar. An elastic spring of force constant K, which is 200 newtons per meter, is stretched through 0.8 meters within its elastic limit. So extension produced 0.8 meters within its elastic limit. Calculate the energy stored in the string. This is just like the previous question. Energy stored in the spring, question mark. So we use the formula straight. Energy stored in an elastic spring is half Ke squared. That's going to give us what? Half times 200 Newton per meter times what? Half times 200 Newton per meter times 0.8 meter times 0.8 meter. So half times K times what? E times E. I'm doing half times K times E times E because E is squared. So half KE squared will give us what? Half KE squared will give us, okay, that will give us 100 times 0.8 times 0.8. So Newton meter will cancel meter. I have just 1 Newton meter left. That gives me what? 100. 2 in 200, 100. That gives me 100 times 0.8 times 0.8 Newton meters. That's 100 times 0.64 joules. 1 Newton meter in physics, first times distance, 1 Newton meters is equal to 1 joules. So we can change our SI unit from Newton meter to joules straight away like that. So that's what 64 joules. The energy stored in the spring is 64 joules. 64 joules. That's the energy stored in the spring. Take note. Number 16 says a spring of force constant 1500 Newton per meter. Let's go. Number 16. A spring of force constant 1500 Newton per meter is acted upon by a force, is acted upon by a constant force of 75 newtons. Calculate the potential energy stored in the spring. Is acted upon by a constant force of 75 newtons. Calculate the potential energy stored in the spring. Elastic potential energy stored in the spring is the same thing as work done in extending the spring. So I think here first thing we need to do is write the formula. W is, I'll find the extension. What's the extension that will be produced with this force? What's the extension? The extension produced from F is equal to KE. From F is equal to KE. Hold on, don't write here because I want to show something. Constant force. The question says constant force. So let's see whether we'll get the answer if we just use it straight without introducing our half. So F is equal to KE. It should be small letter E. Using F is equal to KE. Using F is equal to KE, I can rearrange to say KE is F and what? And E is F over K. E is F over K. So that means extension will be 75 over 1500. Everything is in SI units, so I can substitute my 75 over 1500 straight. This is in SI unit, Newton per meter. This is also in SI unit, newtons per meter. So what does that give me? What does that give me? Okay, let's now go to the formula. Work done is what? Half FE. So that gives me what? Work done is 1 over 2. I want to try this, whether it will work, because it says constant force. I think with constant force, we should not put the half. But let's try. So that's what? Half times what? Force is 75 newtons. Then the extension is what? The extension is 75 over 1500. The extension is 75 over 1500. Does this give us the answer? Let me check. Okay. 0.5 times 75 times 75 divided by 1500. 1.875. Okay, so our work done is 1.875 newtons, which is approximately equal to 1.9 newtons. So the energy stored in the spring is equal to 1.9 newton approximately. So the half will still be there, even though it is said that the force is constant. You still put the half, except you are using a graph and it really shows that the force extension graph is rectangular. We will get to that later. Okay, number 17. When a force of 50 newtons is applied to the free end of an elastic cord, an extension of 4 centimeters is produced in the cord. Okay, number 17. Force of what? 50 newtons produces an extension of 4 centimeters. First of all, 4 centimeter is not the SI unit of length. So we can change this to SI unit by dividing it by 100. That will give us 0.04 meters. Can you see that? So force of 50 newtons produces an extension of 0.04 meters. It says calculate the work done on the cord. Work done on the cord is average force times extension. So although it said that the force is constant, although it was said that the force is constant in this question, we were supposed to, just find its average. We were supposed to just find and use its average. So introducing our half was still fine. All right. So half F here will be equal to half times 50 newtons times 0.04 meters. Okay, so that gives you what? 50 times 0.04. That's a 2 Newton meter over 2. So that gives you 1 joule. Work done is 1 Newton meters, which is equal to 1 joule. The work done on the cord is 1 joule. So that ends question 17. Question 18 now. A spring of length 25 centimeters is extended to 30 centimeters by a load of 150 newtons. Okay. Number 18. When the load is 150 newtons, the spring was extended from its original length of 25 centimeters to a final length of what? 30 centimeters. The question now says, by a load of 150 newtons attached to one of its ends, what is the energy stored in the spring? That's a simple question. So we just need to find the extension. Extension is final length minus original length. That's what? That is 30 centimeters minus 25 centimeters. So 30 centimeters minus 25 centimeters is equal to 5 centimeters. Now, note that centimeter is not the SI unit for length. So you divide by 100 to change it to the SI unit, which is going to give you extension as 0.05 meters. So what is the energy stored in the spring? Energy stored is the work done on the spring, which is the average force applied times the extension. So that's 1/2 times 150 newtons times 0.05 meters. 150 times 0.05. What does that give us? 150 times 0.05 divided by 2. Okay, that gives us 3.75 Newton meters. 1 Newton meter is the same thing as 1 joule. So the energy stored in the spring is 3.75 joules. Take note of that. Okay, that was number 18. Number 19. The energy contained in a wire. The energy contained in a wire when it is extended by 0.02 meters by a force of 500 newtons is, okay, I think that's pretty straightforward. 19. Extension, okay, force of 500 newtons, extension 0.02 meters. Energy contained is work done by the force, which is the average force applied times the extension. I think I got my values right. 500, 0.02 meters. Let's go. So this gives me what? This gives me energy content will be half times 500 newtons times 0.02 meters. So, okay, 500 times 0.02 is just like 5 times 2. So that's 10 over 2 newton meters. I'm doing this first, 500 times 0.02. So that gives me what? 10. Then 10 over 2 will give me 5 newton meters, which is the same thing as 5 joules. So the energy content in the elastic material or wire or rubber is 5 joules. Take note of that too. Number 20, a spiral spring is compressed by 0.03 meters. Calculate the energy stored in the spring if its force constant is 300 newtons per meter. A spiral spring 20. Number 20, a spiral spring is compressed by 0.03 meters. Calculate the energy stored in it if its force constant is what? If its force constant is 300 newtons per meter. Okay, energy stored is the same thing as work done on the spring, which is equal to half Ke squared. So that will give us half times 300 newton per meter times 0.03 meters times 0.03 meters. So I think this is pretty straightforward. You can do it yourself, senior. Meter will cut meter, so you have newton meter as the only unit left. Is that right? Then press your calculator to get your answer. I don't need to finish this for you. You can finish it yourself. Your answer will be a value in newton meters, and that same value can be changed to joules. Just change newton meter to joules. Number 21. Let's move fast. The exercise is a bit long. Number 21 says, calculate the work done to stretch an elastic string by 50 centimeters if a force of 12.5 newtons produces an extension of 5 centimeters on it. Okay. A force of 12.5 newtons. A force of 12.5 newtons produces an extension of what? A force of 12.5 newtons produces an extension of 5 centimeters. So extension produced by 12.5 newtons is 5 centimeters. It now says we should calculate the work done to stretch an elastic string by 50 centimeters. I think we have no problem here. Let's just go ahead and get K. K is F1 over E1. So that's 12.5 over what? 12.5 newton over 5 centimeters. So there's a red flag that flashes in my mind here. Newton is SI, standard unit. But centimeters is not the SI unit for length. So I have to go change that before I can use it. Can you see now? Take note of all these kind of mistakes. So here, what does that give you? 5 over 100 is 0.05 meters. So it is 0.05 meters that I can put here. Can you see? 12.5 over 0.05. What does that give you? 12.5 divided by 0.05. That's 250 newton per meter. So my force constant is 250 newtons per meter. So let's go ahead. The question now says, what work is done when the rubber is extended by 50 centimeters? 50 centimeters is 50 over 100, which is 0.5 meters. So 50 centimeters is 0.5 meters. So I want the work done when the rubber is extended by what? 50 centimeters. I want the work done when the string is extended by 50 centimeters. The work done is half ke squared. I already know the value of k, so my work done is half times what? What's the value of k? 250 newtons per meter. Half times 250 newtons per meter times what? Half times 250 newtons per meter times 0.5 meters times 0.5 times 0.5 meters times 0.5 meters. What does that give me? That will, give you this. Meter divides meter, that goes. Then Newton meter is the only unit left. You just press your calculator to get your answer in Newton meters. You get your answer in Newton meters first. Let me do it for you. This is what? 250 times 0.5 times 0.5 divided by 2. That's 31.25. That's 31.25 Newton meters, 31.25 joules. So the energy stored, or the work done to extend the spring by 50 centimeters is 31.25 joules. Number 22 says a spring of force constant 500 Newton per meter. A spring of force constant 500 newtons per meter is compressed such that its length shortens by 5 centimeters. The energy stored in it is that's also the same. 22. Force constant of the spring is 500 newtons per meter. Okay, I can use indices if I like. It is compressed, and a compression of 5 centimeters is produced. The energy stored in the spring is half ke squared. So this is the same thing, just half times, change this extension or compression to meter by dividing it by 100. So you get 0.05 meters. So my answer will be half times 500 newtons per meter. Okay, let me write that more clearly. Half times 500 newtons per meter times 0.5 meters times 0.5 meters. You get your answer in Newton meter. You change the Newton meter to joule by just changing. And okay, 23 now. Question 23 says use the data in the table below to determine the length x of a wire, assuming Hooke's law is obeyed. Okay. Length of the wire. Okay, from the first part of this table, it shows that when there's no extension, it shows that when no force is applied, that means when the force applied is 0. The original length of the wire is 800 millimeters. So I'm just going to go ahead and write that out. Original length of the wire is 800 millimeters. When the force is 0, that means the wire is not being extended. That tells us that the original length of the wire, there's no force applied on it. Its length is what? 800 millimeters. So that value is the original length of the wire. Okay. Let's now do this. When a force of 5 Newton is applied, its final length became 801.0 millimeters. So let's go ahead and do that. Okay, the final length was 801. The final length was 801.0 millimeters. Let's remove the 0.0 so we just don't make it too long. When the force applied is what? 5 newtons. So look at the table very well. Look at the table. When a force of 5 newtons is now applied on the wire, its final length became 801 millimeters. So that means the extension produced by this 5 Newton force will be L2 minus L1, which is 801 minus 800, which is what? 1 millimeter. Can you see that? So our question says we should find the final length when a force of 50 newtons is applied, because what X means here is that in this question we know the force, because the first row gives us the force applied. So we know the force applied to be 50 newtons, but we don't know the final length of the wire when a force of 50 newtons is applied. So that's what the question just means. So we are looking for the extension that will be produced when a force of 50 newtons is applied. It is this extension that will help us get our final length x, because we add the extension to the original length 800 millimeters to get the value of x. So let's go ahead and do that. We do using Hooke's law, F1 over E1. Now this extension to this extension to the E2 will be x minus L1, which is x minus 800, because x is the final length, but x must be equal to extension plus 800. Are you getting what that means? The final length produced by the final length of the wire when the 50 newton force is hung on it will be equal to the extension produced by that force added to the original length of the wire. So the extension is x minus 800. F1 over E1 is F2 over what? Using F1 over E1 is F2 over E2. What does that give us? That will give us 5 newton. That will give us 5 newton over 1 millimeter is equal to 50 newtons. We said here that 5 newtons produced an extension of 50 millimeters. E1 is what? 50 millimeters. Sorry, I said 50. E1 is 1 millimeters. So we said here already that 5 newtons produced an extension of 1 millimeter. So 50 newtons will produce what extension? Let's make it E2 and cross multiply. So 5E2 is equal to 50. So E2 is 50 over 5. So the extension produced by 50 newton force will be 10 millimeters. That means x will be equal to 800, which is the original length, plus what? 10 millimeters. L1 plus E2. That's what? 800 millimeters plus 10 millimeters. That's 810 millimeters. That's the value of x. Try look at that very well. It's a simple question. Number 24. Number 24 says a wire of length 5 meters. Number 24 says a wire of length 5 meters and diameter 2 millimeter. Okay. A wire of length what? 5 meters and diameter 2 millimeters. Okay, let's change diameter to meter by dividing it by 1000. Okay, that means diameter is 0.002 meters. So a wire of length 5 meters and diameter 0.002 meters extends by 25 millimeter. Okay, extends by 25 millimeter. Extension 25 millimeters. Let's change that to SI unit to 25 over 1000. That will give us 0.025 meters. Okay. When a force of 50 newtons was used to stretch it from its end, calculate the stress on the wire. Okay, force applied. Let me write that on the right. Force applied, 50 newtons. Calculate the stress on the wire. Tensile stress or stress is force acting on the wire divided by its cross-sectional area. So let's go ahead and get the area first. The cross-sectional area of the wire is pi r squared. So how do we get radius? How do we get radius? Radius r will be equal to what? D over 2. That's 0.002 over 2. So the radius is 0. Let me try and split this into 2 so you don't get confused. So the radius is what? The radius is what? The radius is 0.001 meters. That gives you what? Area. Therefore, area will be 22 over 7 times 0.001 times 0.001. So press your calculator. What do you get? 3.142 times 3.142 times 0.001 times 0.001. What does that give us? 1, 2, 3, 4, 5. That's what? 0.123453142 meter squared. So that's the area of the wire. Let's keep that. So stress is what? That means stress is what? We can now use it. The stress is force over area. So what's the force applied? 50 newtons. So our stress will be equal to 50 newtons divided by 0.123453142 meters squared. You can press your calculator to simplify this yourself or check it. So your answer will be in Newton per meter squared. That's stress. I think that is part A of the question. Okay. Second part says the strain in the wire. Let's find the strain in the wire. Strain is extension over length. Strain is extension over original length. So the tensile strain in the wire, tensile strain in the wire. The tensile strain in the wire is the extension produced over its original length. That's a simple question. The extension produced, look up, we got it at 0.025 meters. The original length of the wire, or the length of the wire, is 5 meters. This is the extension produced here, 0.025 meters. Can you see that, seniors? So, and the original length of the wire, and its original length is 5 meters. So strain is extension over original length. There will be no unit in your answer. Meter divides meter. Just get the ratio and put the value here with your calculator. That ends question 24. Okay, 25 now. We're getting close. Question 25 says question 25 says a 50.0 kilogram block is dropped on a spring from a point 10 meters above. Okay, from this diagram, from a point 10 meters above. Okay, I think a diagram will help us here. Okay, this is the block. This is the block. It is dropped on a spring from a point 10 meters above. Okay, let's draw the spring here. It's dropped on a spring from a point 10 meters above. So this point is actually 10 meters from up here. Okay, this is just about energy conversion. It will be easy. 50 kilogram block is dropped from a point 10 meters above on a spring. The question now says, if the force constant of the spring is 4 times 10 raised to the power 4, find the maximum compression. Okay, force constant of the spring, force constant of the spring, K, is what? 4 times 10 raised to the power 4 Newton per meter. The question says we should find the maximum compression. All right. First of all, let me change this to ordinary. 4 times 10 raised to the power 4 is 40,000 Newton per meter. 4 times 10 raised to the power 4 is 40,000 Newton per meter. So let's just keep that. Maximum compression. What this means is that normally when that block is dropped on this spring, the spring will compress a little bit. Let me try. Okay, I think that helps. The spring will compress a little bit. So it's just about energy conversion, because what this means is that during that compression, work will be done. So work done during compression must be equal to the kinetic energy or initial potential energy of the box. So what we are going to say is that the potential energy of the box has a potential energy. From this height, it has a potential energy. When it now lands on the spring, all that potential energy will be spent on doing work in compressing the spring. That's just the physics behind this. So let's go. Potential energy of the box is equal to work done in compressing spring. Work done, let's put it that way, is equal to work done on spring. Potential energy of the box is equal to work done on spring. So I think that helps. The potential energy of the box is mgh. Work done on spring will be half times k times e squared. We've done that several times. Half times k e squared. So, put your values. The mass of this box is 50 kg. Acceleration due to gravity is given as 10. It is at a height 10 meters above. Half times 40,000 times e squared. Okay, it is e we are looking for. So this should give us 500 is equal to 20,000 e squared. So what does that get you? Okay, 20,000 e squared. 20,000 e squared is equal to 50. 20,000 e squared is 50. So e squared is 50 divided by 20,000. So let's go. 50 divided by 20,000, what's that? 50 divided by 20,000, 0.0025. So e squared is what? 0.0025. 0.0025 will be 1 over, I think I'm right here, 2, should be 1 over 400. So E is equal to square root of 1 over 400. So that gives you what? E is equal to square root of 1 over square root of 400. And that's what? Square root of 1 is 1. Square root of 400 is 20. Square root of 1 is 1. Square root of 400 is what? 20. We put 20 there. So E is equal to 1 over 20. So the extension produced is 0.05 meters. I think that's the maximum extension that should be produced. Okay, 0.5. Have we made mistakes somewhere? I don't think these guys are right. The maximum extension produced should not be 0.5. It should be 0.05. Or maybe check my steps if I made a mistake somewhere. Can we take 26? 4%. Let's check. A string of length 4 meters is extended by 0.02 meters when a load of 4 kg is suspended at its end. What will be the length of the spring when the applied force is 15 newtons? Okay, number 26 is pretty straightforward. Let's do it together quickly. A spring, original length 4 meters. The original length of the spring is given as what? 4 meters. The extension produced on it is 0.02 meters. 0.02 meters when a force of 0.4 kg. Okay, 0.4 kg. Now using F is mg. 0.4 kg is 0.4 times 10, which is 4 newtons. Let's just change this mass straight to newtons. We need it here because our second force is in newtons. So the question says, okay, I think I should do this so that I can keep the second set on the right. Let's do this here. So using F is equal to mg. 0.4 kg will be 0.4 times 10, which is 4 newtons. So the first force is 4 newtons. The question now says, what will be the final length of the spring, L3, when the force of extension placed on it is 15 newtons. So what we need to do here is just get E2, get the extension that this force 15 newtons will produce. Are you getting what I'm saying, senior? Our duty here is to get the extension that a 15 newtons force will produce. We know from Hooke's law that what F1 over E1 is equal to F2 over E2. So if a force of 4 newtons produces an extension of 0.02 meters, if a force of 4 newtons produces an extension of 0.02 meters, a force of 15 newtons will produce E2. So we cross multiply. 4E2 is 15 times 0.02 meters. That gives you what? That gives you E2 is 15 times 0. E2 is what? 15 times 0.02 over 4. Let's press our calculator to check that. 15 times 0.02 divided by 4. That's 0.075. So E2 is 0.075 meters. So 15 newtons will produce an extension of 0.075 meters. Let me do that again. 15 times 0.02 divided by 4. 0.075 meters. So the final length of the string will be the original length plus the extension produced, which is what? 4 meters plus 0.075 meters, and that will be what? 4.075 meters. So a force of 15 newtons will give it a final length of 0.075 meters. I think we should be keeping an eye on our options. Our options have been approximated to 2 decimal places. So your answer will be 4.08 meters to 2 decimal places. When doing an exam or when doing an exercise, always keep your eye on the option. There's an approximation required. Okay, that's number 26. Can we take 27? Okay, 27. The diagram below shows the force extension curve of a piece of wire. Force extension curve is force against extension. Oh my God. I think I've lost my page. Let me go search for it. I think I'm back there. Okay. Force extension curve means force produced and extension. Force applied and extension produced, correlated on the graph. The question says the energy stored when the wire is stretched from E to F is. We will take this in the next video. Please, let's just pause here for now. So we'll take the rest in the next video, and I will attach an exercise for you